Welcome to the lesson on section 2.6, Tangents, Velocities, and Other Rates of Change. In this lesson, you'll learn about two limit definitions for the slope of a tangent line, average versus instantaneous rate of change, and finding the equation of a tangent line. In our first example, we'll use slopes of secant lines to estimate the slope of the tangent line for the graph of y equals x cubed plus x at the point 1, 2. In part A, you can easily use a graphing calculator to determine that the graph passes through the points 0.9, 1.629, and 1.1, 2.431. The slope between these points is 4.01. In part B, the slope will be 4.0001. I'm pretty confident that these slopes are approaching 4. We weren't asked to find the equation of the tangent line in this problem, but let's find it anyway. A line with slope 4 that passes through the point 1, 2 has the equation y minus 2 equals 4 times x minus 1. Note that, as shown here, it's highly recommended that you use point-slope form to find equations of lines in this course when you don't already know the y-intercept. Let's see what the tangent line looks like. You can see that the line and the curve intersect at 1, 2, and the line skims the curve at this point. Sometimes we refer to the slope of the tangent line as the slope of the curve. By the property of local linearity, if we zoom in enough on the point 1, 2 on the graph, the tangent line and the graph will be nearly indistinguishable. Now let's look at two ways to describe the slope of the tangent line symbolically using limits. Recall from our lesson on section 2.2 limits that the slope of the tangent line is the limit of the slopes of the secant lines drawing closer and closer to the desired point. We already used this concept to find the slope of the tangent line in the first example. Take a look at the diagram at the top of this slide. 2 points are marked on the graph. Their coordinates are a f of a and x f of x. The slope of the secant line between these 2 points would be f of x minus f of a for the change in y over x minus a, the change in x. The slope of the tangent line should be the limit of this slope as the 2 points draw closer and closer together, or as x gets closer and closer to a. You should write this limit definition somewhere in your notes. Here's a second way to look at the same idea. We have the same diagram as in the last slide, except that the points are labeled x f of x and x plus h f of x plus h. So the change in y is f of x minus f of x plus h minus f of x, and the change in x is x plus h minus x, which is h. As these points draw closer and closer to each other, the distance h along the x-axis will approach 0. You should also copy this limit definition into your notes. Now let's use those limit definitions to find some slopes of tangent lines. For method 1, we'll use the x minus a version. To find the slope of the tangent line to the graph of y equals 1 over x squared plus 1 at the point 0, 1, we'll use a equals 0 since that's the x value of the point where the tangent line and curve meet. So filling in 0 for a in that first limit definition, we get the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Substituting for f of x and f of 0, we get the limit as x approaches 0 of 1 over x squared plus 1 minus 1 over x. We can't just plug in 0 for x right now because it makes our expression undefined. To evaluate, we might find it helpful to eliminate the denominator x squared plus 1 by multiplying it through the numerator and denominator. Simplifying, we end up with negative x squared over x times x squared plus 1. This reduces to negative x over x squared plus 1, allowing us to plug in 0 for x. So the slope of the tangent line at 0, 1 is 0. Using the second limit definition, we would again use a equals 0. Notice that substituting for f of h and f of 0 results in the same limit as in method 1, so the remaining steps would be the same as above. These won't always look the same. Do you know what caused them to look the same here? In example 3, I'm foreshadowing some ideas about velocity and acceleration that will become more solidified in a later lesson. The graph shows a car's velocity. In part A, we're asked to determine when the car was stopped. You would expect the car's velocity to be 0 when it stopped, so the velocity is 0 at point B. For part B, we need to determine when the car was accelerating and decelerating. Accelerating is an increase in velocity, so the car accelerates from start to point A, B to C, and D to the end. The car decelerates when the velocity is decreasing, from A to B and from C to D. In part C, at points A, C, and D, the velocity changes from increasing to decreasing, or vice versa. This means that the car is changing from speeding up to slowing down, or slowing down to speeding up. Speeding up would be positive acceleration, and slowing down is negative acceleration. So the acceleration is changing sign at these points. At point B, the velocity reaches 0, and the acceleration is still changing sign. So at point B, the car stops and then starts again. In this example, we need to identify locations for A and B so that the slope at A is less than the slope at B, which is less than the slope between points A and B. The easiest way to make this happen is to find a location for A that makes the slope negative, a location for B that makes the slope 0, and then we need the slope between A and B to be positive. Here's one possibility. This concludes the lesson on section 2.6, tangents, velocities, and other rates of change.